Okay, so welcome everybody to a new Kickstarter Colloquium and Happy New Year, because this is the first Kickstarter Colloquium of 2023. Just to begin with our usual range of reminders before we get to our speakers, the colloquia is going to be recorded, so if the speakers are happy with that, and the recordings are going to be posted to YouTube for the benefit of a wider audience. So if you prefer not to be recorded, then please keep your camera off. And in the interest of having being able to hear the speakers clearly throughout the talk, please mute your microphone if you're not the one actually speaking. You can use the Zoom chat function to post questions at any time throughout the talks. After each talk, we'll have time for questions and discussions. And if you, once your question is called on, if you could kindly repeat your question so that the recording can hear what the question was before the speaker tries to answer, that would be great. Thanks. So moving on to our speakers, today we're going to get our colloquium series for the year off to a great start with no less than 3 excellent presentations. So I'd like to give a warm welcome to all of our speakers. First up, we will have Kelly Hambleton, who will give us an overview of the TVS Science Roadmap that has come to fruition really through her leadership. And I'd like to emphasize that this is a mammoth undertaking since it covers such an enormous range of topics, and she has very graciously organized and corralled all of the many contributions from many, many TVS authors. Our second speaker will be Saša Simić, who will discuss some of the challenges presented by the LSST's data volume and how his team are meeting that challenge by developing a cloud-based open access storage system for LSST Science in collaboration in teams in Serbia and Croatia. And that facility is going to be a tremendous resource for all LSST research. And then we will move on to addressing one of astronomy's most pressing questions. Siegfried Eggl is going to describe how the launch of large constellations of man-made satellites into low Earth orbit could severely hamper the discovery of solar system objects by LSST if we don't adopt some mitigation efforts. That's a very serious issue indeed. So without further ado, let me invite Kelly to share your screen again, and we can get on with our first talk.
All right, thanks, Rachel. All right, can you see my screen?
We do.
Perfect. Okay, thank you so much, Rachel, for that very gracious introduction. So I'm going to give an overview today on the roadmap. I'm going to talk a little bit about how it's divided, talk about some of the science cases, and give also an update on where we are at the moment. So I would be remiss if I did not show you all the names of all the authors that have contributed to this roadmap. So as you can see, there are a lot of people that have been spending their time and taking and providing much effort into really moving this roadmap forward. So as of now, there are 74 listed authors on the roadmap. So really a lot of hard work and effort has gone into this. And I actually took a look back into my emails to try and figure out when the first discussion of this roadmap was. And it turns out it was January 15th, 2018 was the first mention where Federica stated in one of the meetings that she wanted to have a roadmap for the TVS. And so shortly after then, about a week later, she sent out a list of questions that she wanted addressing, and also provided a layout for the original roadmap that was on Authoria. Later, it went over to Overleaf, but you can kind of get an idea of how long this has been going on for and the effort that has been going in. Unfortunately, due to COVID, it kind of took some time out for maybe a year and a half to 2 years. But that's why after all this work that was done, I decided to try and get a Kickstarter proposal grant so that I could actually finish off all this hard work that's been done by so many people. Okay, so here's what it looks like. This is the front page, and it has actually been on archive now since August. I submitted it along with doing a talk at the IAU, which was well received. And at the moment, we're in the process of trying to get it published at PASP. Okay, so the purpose of the roadmap is to provide a detailed overview of the diverse scientific goals of the TVS. So we all know that TVS has a lot of different scientific goals, and so we tried to organize that into several different sections, including a section that covers the wide, fast, deep survey, the deep drilling fields, the mini surveys and micro surveys. We also have a chapter on methodology and infrastructure, and then the equity and inclusion in Rubin LSST as well. So the layout that we have as of now, which is the version that has been submitted to PASP, has an abstract introduction, a section for time critical science, so that's science that requires alerts. A non-time critical science, that's the science that are going to be using the annual releases more often and does not require alerts for notifying of science. Deep drilling fields, mini and micro surveys, methodology and infrastructure, equity and inclusion, and then there's a summary and next steps. So that's kind of how we decided, or at least Federica decided in the start of the roadmap, that this would be the layout. So in the main survey, we've separated all science into time critical and non-time critical. So there are two separate chapters that cover the main survey, that cover the time critical and non-time critical sciences. And it was kind of decided this way because while there are some science goals that really need time critical and non-time critical science that cover the same kind of objects, there is a lot of differences between the follow-up needs and the requirements for these two separate types of science. And so for consistency, it was decided that it will be split up into these two themes. And then within time critical and non-time critical science chapters, we also have extrinsic transients and variables, intrinsic transients and variables, and also extragalactic variables. So all of these subsections are within these chapters. So the reason for the time critical chapter being a standalone chapter was because time critical infrastructure requirements include rapid delivery of broker alerts and response to those alerts, cross-matching with alerts from other major surveys, facilities, particularly at other wavelengths, customizable alert filtering, rapid reaction follow-up, observing programs, observing facilities with flexible queuing systems, and the need to incorporate gracefully with the target of opportunities. So that's really something that needs to be considered in depth, the target of opportunities and how we're going to have the queuing systems include those, and so that they're not taking up too much of the time. And then software coordination and facilities of to facilitate large-scale programs. So there's a lot of considerations for time critical infrastructure requirements, and that is something that's addressed after each subchapter. So for each science case, so for example, binary stars, AGN, after each of those science cases, there is a section in the roadmap where the requirements for time critical or non-time critical follow-up are discussed. And so for non-time critical science, there are still infrastructure requirements, but those are quite different to the time critical science. So they include, for example, cross-matching with current surveys and ongoing surveys, for example, Gaia and Eggl. There's also going to be a need for large-scale database queries and modeling analysis. There's also going to be co-surveys that are going to be ongoing to try and fill in the gaps so that we have a higher cadence for our data. Simultaneous observations in complementary wavelengths is something that's going to be necessary, but again, it's not time critical. And then the need to gracefully interweave time critical and non-time critical science so that everybody obtains the follow-up data that they need. So as I say, the time critical and non-time critical science chapters are divided up into three different parts, one of them being extragalactic. So the extragalactic subsections include supernova, for time-critical science, intermediate luminosity optical transients, tidal disruptive events, gamma ray bursts, blazars, and electromagnetic counterparts of gravitational waves. And then for the non-time critical science, for extragalactic, we have blazars and supernovae. And then when you're talking about galactic intrinsic variables, we have young eruptive protostars and compact binaries for time critical. So interactive compact binaries. And then for the non-time critical, we have, for example, pulsating stars, galactic globular clusters, brown dwarfs, eruptive variables, young eruptive variables, compact binaries, again for the non-time critical aspect, luminous blue variables, and light echoes. And then finally, we have the time critical and non-time critical chapters separated again into for extrinsic variables. So these include variables such as microlensing events and eclipsing binary stars and the search for extraterrestrial intelligence for time critical science. And then for non-time critical science, we have transiting exoplanets, eclipsing binaries, and microlensing again. So that was the main survey structure for those two chapters. And then we also have another chapter on methodology and infrastructure. And this includes a lot of details on the infrastructure for time critical science, which includes things like the LSST alert stream and also broker alerts. So there is quite a bit of time dedicated to brokers in this section. So if you're interested in using brokers and you don't know, for example, which broker might be useful for you, there is an extensive list on all the brokers available, and then any information that was online or that we were aware of, that's included in the TVS roadmap. So if you know you're going to use brokers, but you're not quite sure which, it's definitely worth taking a look for that. Then we also have some work done by the classification and characterization subgroup, and that's included in this methodology section. And then multi-wavelength characterization and counterparts, and anomalies and true novelties as well. So a lot of information in this chapter. So we also have a chapter on JEDI, that's the final main chapter before the summary. And that has the goal of ensuring, so JEDI is the Justice, Equity, Diversity, and Inclusion subgroup. And it has the goal of ensuring inclusion and diversity in all of the activities of the TVS. So some of the aspects that are discussed in the roadmap are, for example, improving accessibility through the sonification and 3D rendering of LSST data. They work to recruit diverse cohorts of members. They work to enhance the involvement of LSST by including minority serving institutions. They work to collect and retain and publicly release anonymized TVS demographic data. So we all just filled out the TVS survey that was looking to understand demographics. And so that was also a part of the JEDI work. And then the development of best practices and guidelines, for example, for hiring and establishing formal structured mentoring relationships to pair senior members with the new members. So really, they have a lot of great work, and it's all discussed in the roadmap. So just as a quick visualization, here are the contents. So you can see for the original version that was submitted to the archive, it's quite an extensive piece of work. Of course, when we put it into journal format, the number of pages reduced, but actually including the references, it was over 200 pages on the archive. So a lot of great information in there if you're interested in taking a look. Okay, just to give you a quick overview of some of the science cases, there are so many great science cases in this TVS roadmap. So if I don't cover your science case, it's not because I didn't find it interesting. Actually, some of these science cases were selected based on their applicability to the session that I was presenting this at the IAU. But really, there are so many great science cases to choose from that if you're interested in any of these or any of the science cases that I discussed, I really encourage you to take a look. So tidal disruptive events are going to be Very exciting with Rubin LSST, where they're going to probe the origin of the optical emission and then increase the number of well-sampled TDEs. They're going to help, the data are going to help determine the masses of black holes, identify potential host galaxies of the TDEs. They're going to allow us to understand the redshift evolution of the TDE rate and also the black hole occupation fraction. And so I have a diagram here that was included in the roadmap, and it's just a color diagram, but it shows how nicely the TDEs separate from the other types of objects, for example, like AGNs and supernovae. Then we have interesting work coming up about the electromagnetic counterparts to gravitational waves. And so the benefits of using LSST as well include that we will be able to identify the host galaxies. It'll help us with the determination of the source's distance. It will enable the characterization of the progenitor's local environment and also help break the model degeneracies between the distance and inclination. So a lot of great stuff is going to come out of this science. So for supernovae, there's a big group that are working on supernovae, as we all know, and some of the great things are going to be that we're going to increase the number of known supernovae and improve the classification schemes that are already out there, learn hopefully to predict supernovae events and associate them with their host galaxies. A more complex, a complete understanding of the formation history is something that we're going to be working on, and then understanding the evolutionary scenarios. And then finally, of course, supernovae can be used as distance indicators, and this is going to be something that we're really excited about.
Kelly, a gentle time check.
Yeah, okay, thanks. Just a couple minutes. All right, brown dwarfs. There's going to be, we're going to significantly increase the number of brown dwarfs. So right now, for especially the cooler brown dwarfs, we can only get out to distances of, say, 24 parsecs. And so for especially these cooler brown dwarfs, we're going to increase the sample significantly, get the distances and luminosities, and we're going to improve our understanding of the weather patterns. For example, brown dwarfs have been found to have aurorae. And so hopefully we'll see more of that. Eclipsing binaries, short period eclipsing binaries are going to be really moved forward with these data. So here are some examples of short period binaries with in the deep drilling fields, and you can see that we get really great coverage when we phase the light curves. And so for short period binaries, contact binaries, this is going to be a really great mission, especially after the 10 years. And then we're hoping to identify some of the rarer stages of evolution that we don't usually get to see in with other data. And I would be remiss if I didn't include pulsating stars. So for pulsating stars, we have a lot of goals, including to update the pulsating HR diagram, which is what you see here, where you have temperature and luminosity on the axes. So especially for the longer period variables, we're going to hopefully identify new types of pulsating stars and determine the structure of the studied systems. For example, in the bulge and in the cloud, we're going to be using RLIRES to update the structure, and Cepheid stars. Constrain the coefficients of the period luminosity and period luminosity color relations, extend our census of ultra-long pulsators, and the period luminosity relation for long period variables. And just as a quick update as to where we are right now, we have received our review from PASP, and there are a couple of main points. They have asked us to try and reduce the amount of jargon we have, to include a table of contents, which was removed when we updated to the journal layout. So we'll just have to add that back in. Reference other Rubin LSST roadmaps, address some inconsistencies between numbers and sections, and find a proofreader, which I have actually already done from Villanova University. And so we're well on the way. We're hoping to resubmit by the 10th of February is our current internal deadline. And so if you are interested in downloading the roadmap as it is, we have the archive version. You can just use the QR code right here, or just wait for the release of the the past version, but as of now, we already have 4 citations. So I think it's going to be great when it's done. All right, thank you, everyone.
That's tremendous, Kelly, and congratulations on getting such a mammoth publication into print. It was a really impressive piece of work.
Well, thank you, everybody, for all your help and all your hard work. It's been a really great collaborative effort.
Terrific. Well, in the interest of time, I'm going to suggest that we move on to our next speaker. And if you have any questions for any of the speakers, please feel free to use the chat function of the Zoom call at any time, and we will have a discussion session at the end. Okay, thank you very much, Kelly, once again.
Thank you.
And our next speaker is Saša Simić to talk about the regional storage support for LSST research. Go ahead, Saša.
Okay, thank you. Do you hear me?
We do, and we see your screen. Go ahead.
Okay, thank you very much. Well, as you can see, the title of my talk is Regional Storage Support for LSST-related Science. This is also the title of our Kickstarter project. At the beginning, I will just give a short list of the activities which Kickstarter project support. We choose to just a moment. We choose to apply for equipment and software costs. Also, as we know, the Kickstarter project eligible for applying for Kickstarter projects are individuals, teams, or partnership. So we organize the partnership of 2 teams. One is from Serbia and the other team is from Croatia. Both teams has 3 institutions. For example, in Serbian team, there is a Faculty of Science in Kragujevac, which is PI institution, and also there is Astronomical Observatory in Belgrade and Faculty of Mathematics also in Belgrade. From Croatian side, there is also 3 institutions: Department of Physics in Rijeka, Ruđer Bošković Institute in Zagreb, and Hvar Observatory of the Faculty of Geodesy in Zagreb. Our main goal is to improve readiness of teams by increasing the capabilities of data storage and processing. Both our teams and Serbian and Croatian teams has their in-kind contributions to the LSST, and as you can see on this graph at the right side, we organized our teams as it is given in this graph. CPG team, Croatian team, and Serbian team, they are connected to the LSST Rubin Observatory, and they are also connected to the our data center, which we find that it is very important to have during the process of computation and work with LSST telescope, which will become operational soon. Both teams has their own supercomputer, access to the supercomputers. For example, Serbian team has access to a supercomputer in state-owned data center in Kragujevac, and Croatian team also has access to Bura supercomputer in Rijeka. But what is missing is some place where all data from the computation and from the LSST can be stored, and therefore we find that it is very good to have some cloud center. I will switch now to explain in a little bit more detail about the hardware and software component. To realize this task, we select a producer from Taiwan, which is based on our knowledge, producer with a very long experience in producing the data storages. So we purchase the given list of hardware here, and it is also accompanying software, which allows us to have all necessary services for use. Here is some of the images of the our data storage. This is the bay for hard drives. These are some of the hard drives we have, and this image is when it is all joined together, placed in faculty rack with other servers. This is a power supply, and here how it looks like in functionality and operation. But what is more important to us is the software component of this server. The software component is what we are dealing for, and I will now just give a brief description and properties of this software, which is supplied together with the hardware, and that is very good because it's offered a very lot of different functionality. The system which QNAP produced is based on Linux operating system, so it is not so difficult to work with. Data are organized in the home directory, and user can access it when it log through. For example, we can log through web interface browser. Here just some images of the environment. This program file station is something like similar to file manager and allow us to manually manage the data, but there is more clever way to manage the data. For example, automatic synchronization is also possible in this server. Synchronization of data from the computer or computers to the server allow us to have always newest version of our data. It is not so difficult to implement this functionality. It is necessary to install a client software on a computer and set up the name of the server, credentials, and pair the directories. That process is about 10 minutes, and it is everything what user need to do. Everything else is almost automatically, and work is very important. Also, there is a possibility to use not just QNAP software, but also software from other producer, third-party software, for example. And here is an example how to back up your data from the local hard drive to server. In this program, you just need to set up a location for data on computer, local computer, or on server. Address of the server is not so hard to place. Put your credentials, and then you can copy your data to the server. The server also allows work with mobile devices like mobile phones or tablets. There is also software for that, and that is very convenient for quick examination of data. Here is some example. I'm not going to go into details about this. It is very simple. But what is very important for us, especially when you're working collaboration or teams, it is to use shared directoriums. Shared directoriums allows a team or group of persons to share their data and files between themselves. The directoriums are outside of the home directories of the user, and administrator of the system give rights to a particular user for accessing the data. That is very convenient, as I said, which allows multiple users to get access to the data at the same time. Also, shared directoriums can be used with a lot of different softwares, can be used from programming languages like Python or C, and they do not disturb the security of the system. To use shared directoriums, it is very simple. You can just type address of the server, and this particular example use webdav service to access the shared directorium public, type your credentials, and that is all you need to do. If this directorium is accessed multiple times, then it is good to make a network drive, to very simple in Windows operating system. Same it is in other operating system, and you have your shared directorium listed in other drives as well. Also, as I said, this server allows us to access the data from programming languages, and that is very nice because we all make some programs and make some software. This is the example from Python. As you can see, we use the FTP service to access the files, and that is very simple, 3 lines of code, and you can have the data's files and directories listed what you want. Also, very important and very convenient feature is web server, which is included in software supplied from QNAP Reducer. The web server allows to implement a web page on our data server. And that is very nice because all data stay at the server and can be through user interface shared with the users or presented also with through web page, etc. That is very good because all data are on the server. They do not need to be relocated at this from server one server to another, or to share the links. All data are on the server and can be directly presented through web server. Security of the system is very important in today's world. The security is a very big issue, and this server which we have implemented has a very decent protection system from any irregular attempts to log in, attacks, whatever. There is a number of different security levels. I'm not going to go into details about this, but one of these is, for example, very useful IP protection, IP access protection. It means that if someone attack or try to log in from some IP address more than 3 times, then that IP address will be blocked. Initially, I set up the server for blocking this IP address for 1 hour, but after a while, when I realized how often attempts or attacks are, then I increased this to indefinitely, because the number of attempts are not just 1 per day, but dozens of hundreds or hundreds per day. So that means that protection and security of the server is very, very important. Also, there is another way to protect, very similar to IP protection. There is account protection. When you to protect your account, if someone wants to use your account to log in, then there is a 3 times to can type attempt access, and then the account is blocked. Also, there is other ways to protect the data, for example, SSL certificate, but Until now, I didn't implement that because I think it is not necessary. Of course, password protection is maybe the best. You have good password strength, then it is a good way to protect your data. This server allows different ways to include letters, characters, special characters, etc., length of the password, and that is a very nice feature. Also, to increase the protection of your data and working of the server, there is a VPN service which is installed and run on this server, and this is virtual private network. It is a service which allows user to from other side of the local network to be recognized as a local user, and that allows user to have all benefits of the local network and at the same time protect the server from the unauthorized behavior on the internet. To use this protection, we need just to set up VPN connection. That is not so hard to do. Set up the name of the server, some shared pre-shared key, and that is all you need to do. You can access then shared directoriums, for example, in this way by typing in the, for example, Explorer, any else, type this address and the name of the shared directory. But another way of protection is protecting the server against the malfunction of hard drives. And as we know, the server is consisted of a number of hard drives, which are electromechanical devices and can fail during time of usage. So it will mean that all data from one drive will be lost. There is a more clever way to prevent that, and it is called RAID system, or redundant array of independent disk. Our servers support this functionality, and I'm not going into details about this, but I have chosen RAID 5, which allows server to to be secure against failure of one drive, and all data, if one drive is failed, all data will be preserved in others, and same time allows very decent speed of access and redundancy of the data.
Saša,
At the end,
sorry to interrupt, a gentle time check.
Okay, thank you. I'm finishing. At the end, I would like to give just a conclusion. The aims of this project are to install the data storage for the purpose of supporting the intermediate and final data products of the LSST for Serbian and Croatian teams, which are connected to the LSST, to develop the astronomy at the University of Kragujevac, which is the institution with the least developed area of science, and to develop a regional scientific cooperation between both teams. We accomplished all these tasks. The first I also already explained the installation of this server. The second one, we have promoted the project to students, and we have found some interesting students. They are on basic studies, so we are monitoring their improvement, and in time we will engage them in more activities with us. And also I would like to say that we have publicly presented our project in few places, for example, at fifth conference of active galactic nuclei and gravitational lenses in Serbia. We have one day, whole day dedicated to the LSST, where we present this project, in-kind contribution from both teams in Serbia and Croatia. And we have the discussion forum on periodicity mining. We also exchanged visits from Croatia to Serbia and from Serbia to Croatia. Victor and Thomas was visiting those cities. And at the end, we also organized, the Željko Ilić organized a workshop at Plitvice in Croatia, and we were attended at this workshop in October last year. And also today, TVS Science Colloquium is some form of presentation of this project. And at the end, before I end my talk, I would like to ask my collaborators if there are any additional, if they want to say something additional.
Yeah.
Okay.
Hello, Saša.
Hello, Tomislav. Okay.
Yeah. Sorry, Tomislav is here. So I was the part of the Croatian part of the project, and we also received some funding, mainly for the exchange with the University of Belgrade. So we went in Belgrade, and Victor also arrived in Rijeka to promote and to make collaboration. And also at the end, we did a workshop at the Plitvice. It was a second regional LSST Plitvice workshop. There were around 25 participants from the region on the regional level, from Italy, Croatia, Slovenia, Serbia, and Hungary. And we had around 15 talks and presentations. And I mean, the main aim was to promote the collaboration between the groups and in-kind contributions, and between the LSST related science. So this was held in October for 3 days, and we had a great time. And so this was in fact the end of this project.
Okay, thank you, Tomislav. And that will be all for my talk. Thank you.
Thank you very much, Saša and Tomislav. That was a really excellent talk, and quite sobering to realize just how secure these systems have to be to enable researchers to log on remotely. But we all benefit from such systems tremendously. So thank you very much for putting all of the effort in for maintaining such a system.
Thank you.
In the interests of time, I am conscious that we have another talk to get through, so I suggest that we move on to our next speaker, and that if anyone has any questions for Saša or any of our speakers, please put them in the chat, and I encourage our speakers to keep their eye on the chat and respond to any questions that come their way. I would now like to move on to introduce again Siegfried Eggl. This is a particularly important topic that is going to impact all ground-based astronomy, but particularly severely for LSST. So we will now move on to discussing the satellite constellation impact specifically for the Solar System Science Group. So Siegfried, please go ahead.
Thank you, Rachel, and thank you so much for the invitation. So this is really work that has been done by my students at UAUC, and 2 of them were kindly funded by the Kickstarter grant. So thank you so much for having us today. So I think everybody's excited because LSST and Rubin are going to start soon, none more so than Solar System Science community. Why? Because the promise of LSST is to really have an optimized census of the solar system. And that means that we actually are trying to find what is out there and what are those orbits look like, for main belt, for NEOs, for Jupiter Trojans, transient near objects, comets, interstellar objects. LSST is promising to essentially increase the number of known objects by an order of magnitude in almost all categories here. And a lot of effort has been really gone into how can we make sure that LSST provides this? There was a lot of software development efforts where we have new discovery and linking algorithms, and really like, you know, a lot of emphasis on trying to make sure that we provide that sort of census for solar system science to work on for the coming decades. Now, in particular, what's interesting is that LSST is also kind of part of the planetary defense strategy, which means, you know, we want to find all those potentially hazardous asteroids that are still out there. At the moment, we kind of know like roughly 50% or so of them based on the current models that we have, but really with LSST and other facilities that are coming online in the next coming years, we really kind of hope to push this somewhere in the 90% region, so that we can all sleep well during the night and don't have to be afraid of those asteroids, you know, hitting the Earth. But as so often, things aren't quite, you know, working out in the most simple and straightforward manner. And another really booming industry now, which is sort of the space industry in low Earth orbit, has come to interfere a little bit with our plans here. And what you see here is one of the brightest satellites that have been launched recently, AST Space Mobile's Blue Walker 3, and I'm gonna tell you a little bit more about that. But as you can see from this nice picture here, satellites can be quite bright actually. And so constellations of artificial satellites are a reality, and they're probably not going to go away. Some of the more famous ones are, you know, SpaceX's Starlink, and there are a few others out there, and many, many more planned. And those consist of, you know, tens of thousands of artificial satellites per constellation. Overall, I think the current rationale or intentions that the FCC has received is that we're going to have about 500,000 satellites up there by 2035. And if, you know, we don't care about like those, they're going to come and haunt us because they can be quite bright when they are reflecting sunlight. And it turns out that even now, you know, the SpaceX satellites that have been launched are like between 4 and 6 magnitude. But it can be as bright as first magnitude. And I have to say that at this point, satellite operators are putting considerable effort into trying to you know, get the brightness down. We are working together with the IAU Center for the Protection of the Dark and Quiet Skies and the operators to kind of help them mitigate this issue a little bit, and they are willing to do so. But the fact is that, you know, even if they get, you know, magnitudes down to 7 or 8, which is the current recommendation, there's still going to be streaks in the images, and that can have detrimental effects on our science cases. What's also good to know is that, you know, if you are brighter than 6 magnitude, and this has been worked by Tyson et al. For Rubin specifically, then you not only concerned about the streaks that the satellites are causing, but you also have all sorts of nonlinear effects on the CCDs. That can be, you know, quite detrimental to recovering and correction of those images, or simply like, you know, trying to blank out like the stuff that has been overexposed by satellites. And in fact, like if you go to satellite brightnesses that are, you know, kind of near where we've seen satellites so far, there's actually a good chance that some of the CCDs can be damaged. I don't think that's the case for LSST, but some of the other more sensitive CCDs that are going to go online in the next couple of years may actually be harmed. So one of the possible mitigation strategies is, of course, you know, like finding out where those satellites are and then essentially shutting the field of view off for the time that this satellite is passing when it's illuminated by the sun. So as I was saying, like SpaceX is kind of trying to play nice here, and they are putting substantial effort and money into trying to find, you know, better ways how to make their satellites a bit darker. There were some tests with visors that didn't quite work out, but now they're working on coatings and so on. That should help like make the satellites a little less sort of a little more specular, a little less like diffuse, so that you know, when they are kind of redirecting sunlight, it's not everywhere. It's kind of in determined by the attitude and so on. So they're really working on this, and we hope that we can get something together with them. Other companies aren't quite as far along the way. Recently, there was a launch by AST Space Mobile's Blue Walker 3. That is in essence a kind of satellite that's supposed to have direct mobile phone connectivity So you wouldn't need like GSM networks or cellular networks. You can directly like talk with mobile phones to satellites. And of course, that requires a large array of antennas. And, having such a large array of antennas makes a satellite, unfortunately, really, really bright. And this is one of the cases that we've tried to observe at the IU CPS. We found that it's up to first magnitude. In case you're not quite having, magnitude scale in your head, that's about as bright as Deneb or Antares. So that's really like one of the brightest objects basically in the sky, and that's now human-made. The other issue that we found is that these big satellites, they also have like really big launch vehicle adapters. That is in essence like what kind of makes them cling to the rocket, so that satellite isn't loosely kind of connected when they are launching, and those are discarded, and unfortunately those are not tracked at the moment. And for these big satellites, those launch vehicle adapters are also really, really bright. Maybe not quite as bright as the satellite, but this one was like about 6th magnitude, so still brighter than the recommendation that the IUCPS has for those objects. And we don't quite know where they are over time. They eventually decay and burn up in the atmosphere, but they can be up there for years. And so this is the motivation behind what we've been trying to do here. So the idea was basically to see if those satellite streaks in the optimum case where satellite operators get them down below this 6th magnitude, that they don't cause like nonlinear crosstalk in the CCDs, what that would do to our solar system science with LSST. And so we went ahead and tried to figure out where are the observations of solar system objects based on model predictions that we have of both the latest kind of pointings that LSST provides, which is like this OPSIM version 2.99, and a solar system model where we have orbits of solar system objects that we think are out there that we haven't discovered yet. And we kind of combined those together with about 30,000 satellites. That is about the constellation that Starlink is going to launch. It's the version 2 of the Starlink constellation. We didn't include version 1 yet because we didn't have quite enough time to get this through. So we tried to make this as accurate as possible. We have the proper satellite propagator, we have proper orbital propagations for the solar system objects, and also simulating where those solar system objects really are in the field of view at any given time. And what we consider to be affected is if a satellite streak actually enters within 3 arc seconds of one of the solar system object observations. This is based again on the work by Tony Tyson, who figured out like what the kind of full width half maximum of those satellite streaks are, roughly speaking. And that means like that the solar system object would be literally like obliterated by the satellite streak. There are a few caveats here. We don't have crosstalk. We didn't include the moon and earth shine because there's a kind of second order effects. But we do have earth shadowing, so that when the satellites are not directly illuminated by the sun, we don't quite consider them yet. And so our preliminary findings, and this is still preliminary, so please don't quote that yet, is that we kind of confirm one of the recent works by the Rubin team, where they were looking at how many streaks folks would expect at any sort of given observation day from satellites for different sort of observations, and especially the Twilight Neo survey. And what they found was that the Twilight Neo survey is particularly badly affected, where you essentially have one streak in every image, just because you can't really dodge this area effectively if you want to have the observations that lead us to this NEO Twilight survey science. While in the general part, you can dodge satellites if you try hard enough, but there's always a trade-off between dodging satellites and kind of losing time with the slewing and so on, that kind of takes away time from the survey. And so the general consensus was that you can mitigate some of these problems, but especially for the Twilight near-Earth asteroid survey, that's really, really hard. And unfortunately, this is exactly where we are finding most of the affected observations, not only for near-Earth asteroids, but in general. And this kind of means for us that for solar system object observations, these areas are particularly problematic. And that's bad because those are some of the areas where most interesting things happen. For instance, these are the areas where we can see objects that come at us from the sun. So all these kind of asteroids between the orbits of Mercury and Venus, inner Earth objects, and those we really have to try to find in there. And this is where the satellites are most, kind of egregious, I'd say. But also, if we look through the main belt to Trojans, depending on the configuration and the time of year we're looking at. And we've seen actually that for the simulation that we have here, the OPSIM, some Trojan observations were also pretty starkly affected actually by this. On the other hand, the good news is that on a global scale, we only lose about 0.1% of observations of solar system objects. And so you might say, okay, well, that's nothing, right? So that's kind of in the noise. Now, unfortunately, the way that LSST is discovering new objects is that we need 6 observations for those objects to be, all available. And even if we lose 0.1% of those observations, if that's one of the observations that we need for a discovery of the object, that's already sort of an order of magnitude that we lose there. So we're already like in sort of the percent range of the observations and percent range of the discoveries. Let's not forget that this is only the Starlink constellation version number 2. If we go by this 500,000 of planned constellation satellites, then this is about 10 times as many, maybe 20 times as many. And then we are already in a range where we have sort of between several and tens of percent of solar system object discovery is lost. There's also other things that we should be aware of that we didn't consider yet. So for instance, if we have very bright satellites like Blue Boca 3 constellations, and they are aiming for about 160 satellites, we may have to shut off the entire fields once in a while. And that means like it's not only like the streaks that are going through the images, we may lose like entire focal planes at times. And there may also be some possible systematic effects on light curves, even if the satellites are not sunlit, like they're passing by and crossing over asteroids. And while this is really, really quick, they kind of impact the light curves a little bit potentially. And so these are all things that we need to look into a bit more in detail, I think. And I'm almost out of time. So I thank you very much for your attention. If you're interested in kind of joining us, to kind of work on this effort together with industry and together with astronomers, please join the new IUCPS. Thank you so much.
And thank you very much, Siegfried, for an excellent talk on a really important topic. So, and thank you again to all of our speakers. I see we have had a lively discussion in the chat. A few of the questions I think have been answered. So I'd like to call on Bob Eggl, because I think you had a question relevant that hasn't yet been answered.
I had 2 questions. Nice talk. Would 2 by 15 second exposures be better than 1 by 30 to handle this? That's the first question. The other one is the adapters. They don't need to. You don't need to worry about the heat loads on those. Could they be painted completely black?
Yeah, both excellent questions. Let me go to the adapter first. I think painting them black would be really good if we could do that. Also, maybe even more importantly, is to put like small beacons on them so that we can track them actively. So that at least like if they're not bright, if they don't want to make them bright for one or the other reasons, we at least know where they are. So that's something that would be extremely good as an industry standard in any case. And about the 2.15 second exposures. It's also an excellent question. The thing is that we do need the depth, to get to most of the really faint objects. And so you'd eventually, what you kind of lose or win by not having a streak in one image, you kind of lose because you have it in the other one. You have to combine it to go to the depth that we find all those asteroids at. And so I think folks have been looking into this, and I think they've decided that it may not be worth doing the snaps and going with the 30 seconds, because really there's not much gain in taking the 2 times 50 seconds. But that's just my what I've heard. Maybe there's some hands and forth there that I'm not aware of at the moment.
Thanks, Siegfried.
Thanks, Bob.
Thank you. And moving up the chat to some of the earlier questions that came through. Will, you had a question about the TVS roadmap.
I did, yeah, thanks, Rach. Although Kelly, I think, has answered that question in the chat. I'd asked if there are any lessons there might be for other science collaborations trying to pull together something like this, some of which are returning to this after a few years away. And Kelly answered that question in the chat. And I think the point about having specific questions and rigorous guidelines is very helpful. I suspect because people are so busy doing so many other things with their time, then being able to create small bits of effort, I think, towards the goal is important. But yeah, I'd like to thank Kelly for answering that question in the chat.
Yeah, thank you. Specifically, I just felt like the clearer and the more specific the guidelines in advance, the better the authors did in achieving the outcome that was required in a short amount of time. So for the authors that started earlier on, we didn't necessarily have those guidelines in place. And then it took quite a few iterations to get to the final point. So yep, specific and rigorous guidelines.
That's helpful, thank you.
And I see there was a follow-up question from Bob Abel on the roadmap as well. Bob.
Oh, Kelly covered it in a private.
Okay, that
you.
one's been answered. Terrific.
Yes, you did great.
Okay, and I think I see one last comment in the chat from Tomislav, providing the links to the presentations on the regional storage facility. Thanks very much for that, Tomislav. I will link that in the description for when I post the video on the YouTube channel. Siegfried, did you want to follow up? I see Michelle had a comment. Michelle. Okay, Michelle, I'm not hearing.
Sorry.
Oh, there you go. Okay. Hey.
Sorry, wasn't set up for sound. There's this more recently acknowledged background, which I guess will be quite of interest to TVS as well, of these very short duration glints that are coming up with the background of satellites, not necessarily the directly illuminated ones as well, which is interesting, with this kind of 0.4 second flare and sparkle. I guess this is probably a broader question than purely solar system in a way, but I guess it's what characteristics would you like to have well quantified about that population in order to drop them into a model like this?
Yeah, so first we need the attitude of the satellites, because the squintings are or the flaring is mostly due to some sort of unfavorable specular reflection of the satellites, and so that's mostly based on the attitude, but of course also of the material properties. And once we have a better understanding of that, that would really help us. So again, like some of the operators have been really straightforward and very welcoming, in terms of having collaborations with the CPS, and they are going to give us some of the attitude data and maybe hopefully some of the material data as well. And we'll see, how that propagates through the industry, and hopefully if everybody does that, we can model this. We haven't tried it yet, simply because we don't have the attitude data yet. Based on observations, we know that these are there, so they're very well confirmed. But really, we need a better understanding of the satellites themselves and how they are oriented to model this properly.
Thanks.
Let's hope that the industry becomes more forthcoming and open and collaborative in that respect. I know SpaceX has made a start in that direction, but there's many more operators that could use stepping up. Okay, well, thank you very much, everybody. I am conscious of the time, so I want to say a big thank you to all of our speakers today for 3 excellent talks. That was really, really informative. And if you have any follow-up questions, then I encourage you to get on the LSSTC Slack system and ask them directly. Oh, Tomislav, one last comment. Link to the PPT and the video recordings of more extensive talk on the regional storage support can be found in the program of the Plitvice workshop. Thank you very much for that. I will make sure to include those links. So thanks, everybody. And I will see you next time. I would like to note that we are planning to continue this series of colloquia, so please look out for adverts in the future. And I'll see you again soon. Bye-bye, everybody.